Alright, so now let's continue further and now look at the next section, which is chemical basis, and goes over atoms and molecules. And for further information, you go to chemistry wiki page. So all living organisms are made up of matter, and all matter is made up of elements. Oxygen, carbon, hydrogen, and nitrogen are the 4 elements that account for 96% of all living organisms, with calcium, phosphorus, sulfur, sodium, chlorine, and magnesium accounting for the remaining 3.7%. Different elements can combine to form compounds such as water, which is fundamental to life. Life on Earth began from water and remained there for about 3 billion years prior to migrating onto land. Matter can exist in different states as a solid, liquid, or gas. So MES note, matter is any substance that has mass and takes up space by having volume. All everyday objects that can be touched are ultimately composed of atoms, which are made up of interacting subatomic particles. And in everyday as well as scientific usage, quote, matter generally includes atoms and anything made up of them, and any particles or combination of particles that act as if they have both rest mass, which is a portion of mass independent from motion, and volume. However, it does not include massless particles such as photons or other energy phenomenon or waves such as light. We'll discuss those a bit later in this video. And here's a model of hydrogen bonds. This is these ones right here between molecules of water. So this water just has a H2O or 2 H's and an O, and they connect here with these hydrogen bonds. Are just basically different charge strengths across. This one here is more negative on this oxygen and more positive here on this hydrogen, and they go in touch. So the smallest unit of an element is an atom, which is composed of a nucleus and 1 or more electrons bound to the nucleus. The nucleus is made up of 1 or more protons and a number of neutrons. Individual atoms can be held together by chemical bonds to form molecules and ionic compounds. Common types of chemical bonds include ionic bonds, covalent bonds, and hydrogen bonds. Ionic bonding involves the electrostatic attraction between oppositely charged ions or between 2 atoms with sharply different electronegativities, and is a primary interaction occurring in ionic compounds. Ions are atoms or groups of atoms with an electrostatic charge. Atoms that gain electrons make negatively charged ions, called anions, whereas those that lose electrons make positively charged ions, called cations. Alright, so let's unpack all this and go over some of the terms mentioned. So MES note, some of the terms are defined below. Electrostatic attraction or repulsion is the experimentally determined force between electrically charged particles, and electric charge is the physical property of matter that causes it to experience a force when placed in an electromagnetic field. Electric charge can be positive or negative, and commonly carried by protons and electrons respectively. So protons are positive, electrons are negative. Like charges repel each other, and unlike charges attract each other. An object with an absence of net charge is referred to as neutral. And here's an illustration of electric charges and the corresponding field. So in this case, electric fields of individual charged particles or point charges. So you have plus, and by convention, the field points away from a plus charge and then towards a negative charge, like that. So electric field lines of a positive point charge, electric field lines of a negative point charge. Interacting electric fields of 2 charged particles. If you have right here plus and a minus, they're positively and negatively charged particles, so they're opposite signs, or unlike charges, so they are attracting to each other. So notice this arrow is pointing towards the other. And if 2 positively charged particles, they repel because they're the like charges. So notice the lines pushing away against each other. Let's continue further. So an electromagnetic field, also EM field or EMF, is a classical, i.e. non-quantum field. And in this video, I'm not going to be going over quantum mechanics. So basically just basic classical field produced by accelerating electric charges. So notice just a bit of circular reasoning over there. So a charge, electric charge, is a property of matter that causes it to experience a force when placed in an electromagnetic field, and the field is generated by accelerating charges. So it's a bit of a circular reasoning. So anyways, so the electromagnetic field propagates at the speed of light. In fact, this field can be identified as light and interacts with charges and currents. Currents just moving charges. The field can be viewed as the combination of an electric field and a magnetic field. The electric field is produced by stationary charges and the magnetic field by moving charges or currents. These two are often described as the sources of the field. The force created by the electric field is much stronger than the force created by the magnetic field. So an electric field, sometimes called E field or EF, is the physical field that surrounds electrically charged particles and exerts force on all other particles in the field, either attracting or repelling them. So yes, here is an example here. So here's rising up. So effects of an electric field. The girl's touching an electrostatic generator, which charges her body with a high voltage, which is voltage is electric charge density or pressure. So just this is high amounts of charge condensed into a small area. Her hair, which is charged with the same polarity, is repelled by the electric field of her hair and stands out from her head. So yes, you have it's charging it up, and these all build up the same charge, so it just wants to all separate and move away. So her hair's flying away. A magnetic field is a vector field, and a vector field is just a magnitude / direction assigned to points in space. That describes the magnetic influence on moving electric charges or electric currents and magnetic materials. A moving charge in a magnetic field experiences a force perpendicular to its own velocity and to the magnetic field. The term, quote, magnetic field is used for two distinct but closely related vector fields denoted by the symbols B and H. And these B and H fields, here's from another website, just as a good comparison. Just a good way to think about it. So the magnetic field H might be thought of as the magnetic field produced by the flow of current in wires, and the magnetic field B as the total magnetic field, including also the contribution M made by the magnetic properties of the materials in the field. And here's some images to illustrate this. So over here, this is some iron filings right here, just a bunch of small iron particles all around, and this is a horseshoe magnet. So the shape of the magnetic field produced by a horseshoe magnet is revealed by the orientation of the iron filings sprinkled on a piece of paper above the magnet. So this is above it, and you can see the lines, the iron filings lining up accordingly. And just that vector field here is just a mathematical abstraction. Basically, let's say you have a piece of space, or just some space here, then you have a direction and magnitude of a quantity. So in this case, these arrow sizes, these arrow sizes vary across this field, this vector field. All right, continue further. So here is a good way to think about the types of magnetic fields. So the H field can be considered the external. Let's say you have an external field like that, and then you have the internal M field, and then you have the B field, which is a combination of all of them together. So you account for all of them. You have the little, these really small lines or short lines or condensed lines that accounts for this wider one, and this one is super compact lines in this material over there. And here's a comparison of B, H, and M inside and outside a cylindrical bar magnet. And the magnetization factor field M represents how strongly a region of material is magnetized. So that's just the M one. And going further, this is the direction of a charge. So a moving charge in a magnetic field experiences a force that's perpendicular to the direction of the motion and the magnetic field. So going back to the definition. So a moving charge in a magnetic field experiences a force perpendicular to its own velocity and to the magnetic field. So you're going to get something that looks like this. If you have the B field going downwards, then this charge is moving this way, you're going to experience a force F that's going to be perpendicular to B and to this one, and then a positive charge in this case going inwards. But it's always going to be inwards because it's still moving, so in other words, it's going to move around in a circle. So I'll just read that over here. So a charged particle that is moving with velocity v in a magnetic field B will feel a magnetic force F. Since the magnetic force always pulls sideways to the direction of motion, the particle moves in a circle. So it's always moving sideways or 90 degrees or perpendicular from this velocity there, the motion. Alright, and now, as I alluded to earlier, I just want to make another note. MES True Science Note. Yeah, the exact nature of electric charges and electromagnetism is unknown, well, at least publicly, as exemplified by the circular reasoning fallacy in their definitions. So, an electric charge is a property of matter that causes it to experience a force when placed in an electromagnetic field, which itself is produced by electric charges. So, definition of electric charge includes electromagnetic field, which is also defined based on electric charges. So what is a field? A field of what? Is a good question. So a good starting point, however, is to view charges as physical interactions of an ether and the resulting electromagnetic field as a propagation of the resulting disturbances of the ether or aether, like the wakes behind a moving boat. Except the boat itself can be seen as a void in the ether itself. So yeah, this is just a good video from this channel right here. Ionel Dinu. So basically, if you have, I think these are tennis balls with a line connected, you just shake them. Now that could be considered the charge, and then you can so the charge, the motion of that, and then you have wakes or waves spreading across all over from it, and they interfere with each other, and so on. So that's just a good way of viewing it. And yeah, I recommend checking that out. Anyways, let's continue further. So another term that was involved is electronegativity, and this is symbolized as this one here, this X. Is the tendency of an atom of a given chemical element to attract shared electrons or electron density when forming a chemical bond. And likewise, a loosely defined term, electropositivity, is the opposite of electronegativity. It characterizes an element's tendency to donate valence or outer electrons. An ion is an atom or molecule with a net electrical charge. A cation is a positively charged ion with fewer electrons than protons, while an anion is a negatively charged ion with more electrons than protons. Just remember, protons are positive, electrons are negative. Opposite electric charges are pulled towards one another by electrostatic force, so cations and anions attract each other and readily form ionic compounds. So yes, you have different charges. I mean, if you have ions that are positively charged or negatively charged, they will push towards each other and make ionic compounds, or at least are more readily can do that. So light or visible light, just to go over further, so light or visible light is electromagnetic radiation within the portion of the electromagnetic spectrum that is perceived by the human eye. So visible light is usually defined as having wavelengths in the range of 400 to 700 nanometers, or nm. This is a 1/1000th of a meter. Between the infrared with longer wavelengths and the ultraviolet with shorter wavelengths. In physics, the term, quote, light may refer more broadly to electromagnetic radiation of any wavelength, whether visible or not. In this sense, gamma rays, X-rays, microwaves, and radio waves are also light. The primary properties of light are intensity, propagation, direction, frequency, or wavelength spectrum, and polarization. I'll get to polarization in a bit. Yeah, so its speed in a vacuum is this is 299,792,458 meters a second, or m/s. And this speed is one of the fundamental constants of nature. Like all types of electromagnetic radiation, visible light propagates by massless elementary particles called photons that represent the quanta of electromagnetic field and can be analyzed as both waves and particles. The speed of light in a vacuum, commonly denoted c, just go over it in more detail, is a universal physical constant that is important in many areas of physics. Its exact value, and keep this in mind, is defined as this number, so the 299,792,458 meters per second, approximately 300,000 kilometers per second, or 186 miles per second. It is exact because, and this is a big because, by a 1983 international agreement, a meter is defined as the length of the path traveled by light in vacuum during a time interval of, and then this 1 divided by 299,792,458 seconds. So in other words, after 1 full second, you're going to get 1 meter. And so after 1 full second, you get 1 meter, and that meter is defined as using this constant. So in other words, it's just circular reasoning. So note the circular reasoning once again. So that's very interesting. It's for another video of itself that I may like to cover. So anyways, continuing further, so in physics, a quantum, or plural quanta, is the minimum amount of any physical quantity, any physical entity or physical property involved in an interaction. The fundamental notion that a physical property can be, quote, quantized is referred to as the hypothesis of quantization. This means that the magnitude of the physical property can take on only discrete values consisting of integer multiples of one quantum. For example, a photon is a single quantum of light or of any other form of electromagnetic radiation. Yeah, so essentially, if you're looking even at wave phenomenon or light or so on, quanta or quantization, you're looking at a discrete a single value or smallest value, and then you can add up to make the full spectrum and so on. Alright, so now I just quickly paused the video and I just inserted my earlier video, just linked to my earlier article / video on calculus of basically radiation from the stars. Just my earlier post there. It's from the Hive blockchain, and I wanted to compare the different, or just to compare how the mainstream does light quantization with one from a YouTuber called FractalWoman, which is a very interesting one. So, for example, here's the mainstream light quantization, just a simplified version. If you have a flashlight shooting a whole bunch of different wavelengths, and then each one of these would be, let's say, 1 second. After 1 second, each one of these would have a wavelength, and then you have a whole bunch of different wavelengths. But then mainstream would consider each one of these as quanta. So this is quanta, different wavelengths. And then, for example, blue color will have its own quanta. Red would have its own, and so on. Yeah, and as you can see by these images, you have a bunch of different wavelengths there. So a bunch of waves like that. So we'll consider it as one quanta there. So it's a bit hard to grasp the mainstream side of it. And here's just also the wave and particle duality of the mainstream side. So you'll have wave-like that it's wavy, but at the same time you can quantize each amount. So this is discrete, this is same as this, etc. So the particles that it just keeps repeating. And then this is from the FractalWoman YouTuber. Her name is Lori Gardy, and it's very interesting. Her take on light quantization would be, so let's say you have a unit of time, for example 1 second, you're detecting wavelengths. So then the mainstream would do something similar to this, would do something like this. They would consider this after 1 second, this as a quanta. This is one, and then it would consider this one as a longer wavelength quanta 2. So it would consider, or photon 1, this is photon 1, etc. This is photon 2, and so on. And it would say those are what's quanta. But then in her side instead, it would be like each one of these is its own quantization. So this has one here of this high frequency here, and that these are all equivalent energy-wise. So then this one has low energy because there's only 4 of these quanta. This one is high energy, high frequency wave, and that is because there's a lot of these, as opposed to just taking the whole thing as a quanta, which is a very, very interesting take. And I think she might be more right than the mainstream. Anyways, continue further. Alright, continuing further. So in physics, electromagnetic radiation, or EMR, consists of waves of the electromagnetic, or EM, field propagating through space carrying electromagnetic radiant energy, such as these little dots there. And continuing further, so a triangular prism, here's just the image of this prism, just a glass pyramid, or in this case 2D. So a prism dispersing a beam of white light. The longer wavelengths red and the shorter wavelengths blue are separated based on how they bend across this prism there. So notice this is just white light, all the light frequency colors, and then just make it like this. So notice then it separates and you can see a rainbow. But interesting is, so it has it inside there, but here's just a real life image of it, which doesn't look too similar to this actually. It has the separation there at an angle, but inside doesn't look like that. So yeah. But anyways, that's why you always got to compare theory with actual observation. So this one here looks something like this, and also has some other reflections down there. So photograph of a triangular prism dispersing light. That could be from other reflections and so on, because you also have an edge there and so on. So yeah, so it looks like that. So notice how this white light separates from blue and all the way to yellow and so on. Like that. And then towards the reddish side. Yeah, so photograph of a triangular prism or pyramid dispersing light. Actually, in this case, it might be like a sideways pyramid, or not even a pyramid. But anyways, it's a triangle. Going further, here's the spectrum. So these are basically all just different wavelengths, and then the visible one is over here. So you have the all the way to ultraviolet / purplish, bluish, all the way to green, and then red is the lower frequency. So notice the frequency increases on the left side, and then decreases on the right side, and the wavelengths increase on the right, so it gets bigger, farther and farther, like that, go farther and farther, versus the other side goes very, very fast frequency. And there is the visible range here, just between the UV and the infrared, right there. And there's microwave, radio waves, and so on, X-rays. This is gamma rays all over there, and this long radio waves are very, very long. Yeah, which gets into the kilometer side. Because remember, these ones, the visible range was in the nanometers, a billionth of a meter. Now you have radio waves is actually 10 meters. Yeah, oh, this is 10 to the 0. Actually, that's 1. So that'll be 1 meter long. Then you have AM waves, which is 100 meters long, which is very, very interesting. Anyways, this is an electromagnetic spectrum with visible light highlighted. It's right here is highlighted. Continue further. So here's a linearly polarized electromagnetic wave going in the x-axis with E denoting the electric field and a perpendicular B denoting the magnetic field. Because remember, it's a component of both electric and magnetic fields. So notice there, this one is the blue, is the electric one right here. Note, linear polarized just means it's geometrically going in the just linear directions. It's all in one axis there, and then the other side is 90 degrees on the other axis. And here's another example of a circularly polarized. So representation of the electric field vector of a wave of circularly polarized electromagnetic radiation. So this is just the representation of the field, electric field, not necessarily the actual how light is. Because remember, the field is more of an abstract and mathematical construct to define magnitude, such as that force that is experienced with charges and the field. Yeah, so that is circularly, and then here let's just go quickly on polarization. So polarization, also you could write it without the Z, is a property applying to transverse waves that specifies the geometrical orientation of the oscillations. In a transverse wave, the direction of the oscillation is perpendicular at 90 degrees to the direction of motion of the wave. A simple example of a polarized transverse wave is vibrations traveling along a taut or tight string. For example, in a musical instrument like a guitar string. Yeah, so depending on how the string is plucked, the vibrations can be in a vertical direction, horizontal direction, or at any angle perpendicular to the string. In contrast, in longitudinal waves, such as sound waves in a liquid or gas, the displacement of the particles in the oscillation is always in the direction of the propagation. So these waves do not exhibit polarization. Transverse waves that exhibit polarizations include electromagnetic waves, such as light and radio waves, gravitational waves, and transverse waves, shear waves in solids. So just illustrate, here's the transverse wave. So notice that the wave is going up and down, or just away from this. So it's going this way here, it's going to the right. The wave is going to the right, but the oscillation is going perpendicular to that direction. So it's transverse direction. That's a transverse wave. So illustration of a simple plane or transverse wave propagating through an elastic medium in the horizontal direction with particles being displaced in the vertical direction. Only one layer of the material is shown. It's one layer going up and down. And going further, so here's a tight string or taut string. So here's an illustration that you have this this gap there, and you can have it go linearly polarized this way, going back and forth that way. You can also make it circularly polarized. And notice how if you have it tight there, I haven't tried this, but it looks like you can convert this with this linear polarizer. So you spin this this way, and it's going this way. So that's a very good illustration of this. And apparently light can do this too, or similar effects to this, at least with its electric / magnetic components of its of itself. So yes, here circular polarization on thread converted to linear polarization, very, very fast. And so longitudinal waves are waves in which the vibration of the medium is parallel, or quote along to the direction the wave travels, and displacement of the medium is in the same or opposite direction of the wave propagation. So in these cases, when this happens, you're not going to have a polarized setup here. Oh, you can't polarize this, apparently. So plane pressure pulse wave. So this is all going forward. So notice that the line's getting condensed and then decondensed and expand out. Yeah, that's fascinating stuff. Let's continue further. Alright, so now let's continue further. So, unlike ionic bonds, a covalent bond involves the sharing of electron pairs between atoms. These electron pairs in the stable balance of attractive and repulsive forces between atoms when they share electrons is known as covalent bonding. So, MES note, some of the terms are defined below. So, electron pairs consist of two electrons that occupy the same molecular orbital but have opposite spins. And yeah, let's go into what this is. So a molecular orbital is a mathematical function describing the location and wave-like behavior of an electron in a molecule. This function can be used to calculate chemical and physical properties such as the probability of finding an electron in any specific region. So yes, it's a lot of this electromagnetism, chemical analysis, and yeah, light and electrons and so on, charge has a lot of abstract mathematical functions involved, at least in the mainstream theory side of this. So anyway, so here is these are some mathematical functions on there to describe the molecule at different energy levels and so on. So this is complete acetylene, which is this molecule. A molecular orbital set. The left column shows molecular orbitals which are occupied in the ground state, which with the lowest energy orbital at the top. So yes, so it's basically low energy there, and then then they get higher energy at the bottoms over there. The white and gray line visible in some MOs is a molecular axis passing through the nuclei. The orbital wave functions are positive in the red regions and negative in the blue. And yes, you have different charges and probability of seeing the charges and so on in these in these regions. Going further, so the right column shows virtual MOs which are empty in the ground state but may be occupied in an excited state. So here's low energy state is actually the left side, and the top is the lowest energy. And then this one here, virtual ones that show up in excited or higher energy states. You can have something that looks like that. It's fascinating stuff. Well, yeah, it looks like it's similar to if you spin something. You have higher energy, they condense, and so on. But yes, this is just a bit beyond this video. Anyways, continuing further. So spin is an intrinsic form of angular momentum carried by elementary particles and thus by composite particles, which are called hadrons and atomic nuclei. Yeah, and spin is analogous to classical rotation, but has peculiar properties such as elementary particles cannot be made to spin faster or slower, even though the direction of spin can be changed. So yes, so spin is similar to actual rotation, but with some caveats that is different than conventional spinning, such as you can't speed them up on some of these particles. You just change the direction and so on. So anyways, continuing further, yeah, change direction or of the spin. Yeah, that's interesting. You can change direction without changing the make it slower or faster. That's a very interesting take. Anyways, a hydrogen bond is primarily an electrostatic force of attraction between a hydrogen atom, which is covalently bound to a more electronegative atom or group such as oxygen. Yeah, this Wikipedia, this is from Wikipedia, so it doesn't have it complete there. That's why I added this giant sentence here. Because this is saying hydrogen bond is primarily an electrostatic force of attraction between a hydrogen atom, which is already covalently bonded to this one, and it's to another. Yeah, so and another. So it's between this hydrogen one and another electronegative atom bearing a lone pair of electrons deemed the hydrogen bond acceptor. So so this hydrogen is covalently bonded to this more electronegative atom, and then it can connect to that electronegative side of another atom or group of atoms. All right, let's go further. And so a ubiquitous or widespread example of a hydrogen bond is found between water molecules. In a discrete water molecule, there are two hydrogen atoms and one oxygen atom. Two molecules of water can form a hydrogen bond between them. When more molecules are present, as is the case with liquid water, more bonds are possible because the oxygen of one water molecule has two lone pairs of electrons, and each of which can form a hydrogen bond with a hydrogen on another water molecule. And we're going to go over that same image again that I went earlier, but now we're just describing it in more detail. So MES note that hydrogen is made up of a proton, which is a positive charge, 0 or some neutrons, no charge, and 0 or more electrons, which are negative charge. And the most common isotope of hydrogen has 1 proton and 0 neutrons, termed protonium, but barely used. Isotopes refer to atoms with the same number of protons but different number of neutrons. So hydrogen is basically just a proton in most cases, and 0 neutrons, and occasionally an electron or two, or none. Alright, so here's that image again. It's a model of hydrogen bonds. One here, these are the hydrogen bonds, and this is the electropositive. I mean, this is the electronegative side over there on the two lone pairs on the oxygen atom, and there's the hydrogen positively charged wants to attract the negative side over there, and that's how water molecules are connected with hydrogen bonds. So model of hydrogen bonds between molecules of water. Alright, going further. So a partial charge is a non-integer charge value, just to illustrate these, this delta plus and delta minus. So a partial charge is a non-integer charge value when measured in elementary units, or in other words, charge of a proton and electron. Partial charge is more commonly called net atomic charge. It is represented by the Greek lowercase letter, this right here, delta, and namely delta minus and delta plus, or delta plus. Partial charges are created due to the asymmetric distribution of electrons in chemical bonds. Yeah, such as this right here. If you have a plus here and a plus here, and these are two negatives, but they're distributed asymmetrically. So you have a plus side more on this side, and this oxygen atom has more negative on this side over here. So yes, very interesting stuff here. And here is an electron microscope of these hydrogen bonds right here. These little dashes there, and these are exaggerated over here, and you can see them a bit. So atomic force microscopy, or AFM, image of this right here, Naphthalenetetracarboxylic diimide, which is just a solid organic compound, molecules on silver terminated silicon interacting via hydrogen bonding, taken at 76 Kelvin or minus 196.15 degrees Celsius, so very cold. And the quote hydrogen bonds in the top image are exaggerated by artifacts of the imaging technique. So right here it's exaggerated of the technique, but you can have a view of them. So there's the molecules and there's the hydrogen bonds across there. And just note on this chain termination for the silver terminated, just to get more context on it. So chain termination is any chemical reaction that ceases the formation of reactive intermediates in a chain propagation step in the course of polymerization, which is chain of repeating molecules, effectively bringing it to a halt. So it's just a bit more complex than is necessarily needed in this video. So in chemistry, a reactive intermediate or an intermediate is a short-lived, high-energy, highly reactive molecule. When generated in a chemical reaction, it will quickly convert into a more stable molecule, so it's basically an in-between step. And chain propagation, sometimes referred to as propagation, is a process in which a reactive intermediate is continuously regenerated during the course of a chemical reaction, and this is all involved in this atomic force microscopy, just to be able to show this image. A lot of chemical reactions in the middle of it as well.